Hello students, and welcome to topic 15 of alternative and renewable energy sources. The topic we'll be covering is geothermal energy and heat pumps. This is a view of a window air conditioner and an outdoor unit compressor of a split system residential air conditioner. It is referred to as a split system because the system is split. The evaporator coil is inside and the condenser coil is outside. The evaporator coil is the coil that gets cold and cools the air, and the condensing coil is the coil that gets hot and rejects heat to the outdoors. As stated here, an air conditioner is basically a refrigerator without an insulating box. It uses the evaporator of the refrigerant to provide cooling. The mechanics of the refrigerant evaporator cycle are the same in an air conditioner as in a refrigerator. This is a view of a residential split system air conditioner. The vapor refrigerant enters a compressor where it is compressed to a high and hot pressure. It then enters a condenser coil where it condenses from a vapor to a liquid and gives up its heat. It is then forced through a small orifice hole where its pressure is reduced. It then enters the evaporator coil where it returns to a vapor, boils, and takes on heat. It's important to have insight into what affects the efficiency of an air conditioner and a heat pump. The proper terminology is coefficient of performance, not efficiency. The COP, coefficient of performance, is the useful work out divided by the required work in. The coefficient of performance efficiency, there is a better understanding, is related to the temperatures both to the inside and the outdoor. Let's look at the condition of an outdoor temperature of 95 degrees Fahrenheit and an indoor temperature of 75 degrees Fahrenheit. The maximum COP is 26.75. With the outdoor temperature lowered to 85 degrees Fahrenheit, the COP is now 53.5, almost twice as efficient. Now looking at the heat pump, the COP again is related to the outdoor and indoor temperatures. Heat pumps are rated at an outdoor temperature of 47 degrees Fahrenheit and 17 degrees Fahrenheit. At an outdoor temperature of 47 degrees Fahrenheit, the COP is 23.04. And at 17 degrees Fahrenheit, the COP is 10, less than half. Conclusion: air conditioners and heat pumps are very dependent on the outdoor temperatures. It's worth noting that a heat pump can also act as an air conditioner because of the reversing valve. It sends the refrigerant first from the compressor to the outdoor coil in the air conditioning mode and to the indoor coil first in the heating mode. Heat pumps must have an auxiliary means to heat just in case the heat pump fails. The auxiliary heating is also necessary because as the temperature lowers outdoors, the building would need more heat, but just as we have seen, the lower the outdoor temperatures, the heat becomes less efficient and puts out less heat. The point at which the amount of heat the heat pump puts out is equal to the amount of heat that the building needs is called the balance point. As here, the outdoor coil in the heating mode will be well below the freezing temperature. Therefore, the moisture in the air will condense and freeze on the coil. It must be defrosted. This is usually accomplished by running the heat pump in air conditioning mode, taking heat out of the house to defrost the coil. The auxiliary heat, which is most commonly electric coils, then comes on to not only heat the house, but to replace the heat removed by the air conditioner. Geothermal heat pumps depend on the almost even ground temperature, not the outdoor air temperature, and are therefore much more efficient. And the coil does not have to be defrosted. The EPA states that a geothermal heat pump can save 30 to 70% on home heating and 20 to 30% on the home cooling energy over conventional systems. They can have piping that goes into the ground like a well, lay in a trench, or in a pond. They can have groundwater from a well or deep pond or lake and dump the used water back into the ground or to a river or lake. Geothermal heat pumps do not have air blowing over coils. They have water flowing over heat exchangers. The deeper we go into the ground, the more constant temperature is year-round. The average annual temperatures is given here. The thermal conductivity of the soil, which will affect how many linear feet of trench are required for a system. A chart of thermal conductivities is given. A few feet of soil over the piping in the trenches will insulate them from the outdoor air. A ground source heat pump must have three components: a heat pump, an earth connection, and a distribution system. The earth connection can be horizontal trenches, vertical boreholes, submerged into a lake or pond, or use water from a water well. Here shows horizontal trenches, and here shows vertical boreholes. Here shows the earth connection by way of a pond. The earth connection is by water from a well. The water is returned to the ground or dumped into a river or pond. The closed loop can be a vertical borehole, a horizontal trench, or surface water such as a pond. The open loop can be water from a well, injecting the water back into the ground or dumping it into a pond or river. Anywhere in the United States has suitable conditions for a ground source heat pump. If there are any questions, please post them on the eLearn Help discussion.